Okay, so this is the last talk from me actually in this Dara training, and I hope you've had a good time. Apologize for the format being videos. It would have really been nice to be there, but it's just how it is. So yeah, the last talk I'm going to be giving is astrometry. And before really kicking off in astrometry, I just want to go over just a few things on coordinate systems. So I think you had, was it on Monday? You already had a talk by Jamie on coordinate systems. So you saw this image. I watched his talk. I thought it was very good. And I thought I'd steal this image and use it. And just kind of start from this and build from there. So let's say you have your observer here, and you have your equatorial coordinates, so going around and going up, and you have your so let's say you're at Greenwich, and it's the vernal equinox, and this is your meridian line here, and so at sidereal time 00, any sources you have along this meridian, you know that they're at right ascension 0, and you can work out the declination based on the angle from the equator equator there. So yeah, you can work out from that the right ascension and declination of any source. So let's say this is like a two-hour angle, 2 hours of hour angle from your meridian at that time. So you'd have a right ascension of 2, and let's say it's got like a declination of plus 45 degrees or something like that. So you can define the coordinates of some celestial object using right ascension and declination, which is our coordinate system. And if you have a very stable telescope, you can just use this method to kind of look at a bunch of objects on the sky and kind of just give every object a set of coordinates and build like a sky map essentially. This is kind of okay with things like optical telescopes, but you will have had a lecture by now on VLBI, and you'll know that it's not quite so easy to just to just look at things with VLBI. It's not like you don't really have like a camera. You have to use these time delays, and they're very heavily affected by a bunch of different delays and things, which I'll go into later. So you can't really just use the sidereal time to define coordinates of objects in radio. So what you really need is a bunch of objects in a coordinate system that you can use as reference points, and we call this then like a reference frame. So it's basically a bunch of sources that represent particular points on the sky, and we can then measure say you have like some other object now that's that its location relative to one of these points. You can then work out the coordinates of your other object with respect to this reference frame. So I just kind of wanted to reiterate the idea of a coordinate system and why it's important, and then this will become kind of apparent why this is important in radio, because in radio you need to have a reference frame of objects that you work out the relative locations of things with respect to. You need a reference frame. Okay, so yeah, astrometry then is the measure of positions of things on the sky with respect to a coordinate system. And like I said, in the case of like an optical telescope or a very stable telescope, you can kind of do this just using locations and times. But when it comes to a radio interferometer, which is not really a stable telescope, then you need to have this other techniques, which I'm going to be introducing here. So the kind of fundamental difference with imaging using interferometry versus imaging using most other kinds of astronomy is that we don't use like pixels. Yeah, we don't use like point and click camera type things. So in interferometry, we get our source location based on essentially time delays. And throughout this talk, I'm going to be talking in a vocabulary of time delays. In reality, we usually use phase. So you have like, say you have two signals and they're arriving at some point with some time delay, they'll be out of phase, right? If you have two sine curves and one is shifted in time with respect to the other, then you'll have some difference in phase. So phase and delay, they're not interchangeable, but they're kind of proxies for the same thing. And I think as an introduction, it's much easier to grasp the idea of delays. So actually, a lot of the notes in here will be written with the word phase. Whenever you see that, just know that you can also think in delays, and it's fine. So yeah, I think it's just easier to think in time delays. So let's say you have your interferometer and you just have telescope A and telescope B, and they're very far apart, and you're looking at some object up in the sky. Of course, this would be much, much further away in reality, but I don't have an enormous computer screen that goes off hundreds of miles up into the sky. So anyway, let's say your radio source is at the direct midway point between these telescopes on the sky. So if this telescope was looking directly up and that telescope was looking directly up, and you knew those directions and you worked out the halfway point, that's where your source would be. And if this source is emitting radio signals and they're coming in as plane waves, then they will reach, the same waves will reach A and B at the same time, because the radio signal is traveling at the speed of light. And as long as the distance is the same, the arrival time of the signal should be therefore the same. If instead your source is not at that midway point, but it's at some other location, right? So now the radio waves are coming in like plane waves like this, and now they'll reach telescope B before they reach telescope A. Not much big difference because it's not moved much from the midway point, but it's going to be reaching B first by some time delay, some measurable time delay. Now let's say your radio source is even further off the midway point. Now it's going to be reaching B much sooner than it's going to be reaching telescope A. So based on the arrival time difference, you can work out the direction of the source on the sky. And the larger the time delay, the larger the offset your source is from that midway point. So that's kind of written here. So these symbols, so this is phase. So it, like I said before, just think of this as delay. So the delay of the signal arriving at antenna B and antenna A is proportional to the phase term corresponding to the direction where the emission is coming from. So don't get too bogged down with what you see on the screen in terms of equations. Just the concept is more important. Signal arrives at B before A, and the further it is from the midway point, the more that is. So if it were at the midway point, it would arrive at both of them at the same time. So the difference would be 0. Okay, so that's great. Only things are not really that simple. So if you were to have some clouds or something above antenna A, then, oh, hold on, my video is frozen. Sorry about that. Where were we? Yeah. If you have some clouds or something above telescope A, then what's going to happen is it's going to slow down the signal a little bit. So even though your source is currently at the midway point, and there should be no time delay between arriving at A and B, because you've got some clouds and stuff, it's going to slow down a bit, and it's going to reach A a little bit later. So if you were using, if you were assuming there were no clouds and you were using this kind of mentality, you would think, oh, okay, so the source is actually over here. But it's not, right? the troposphere, or the clouds and stuff, the weather above the station, has given us the impression that the source is not where it is. And that's not the only thing to worry about. There's also the ionosphere, because we're talking in radio waves. So the ionosphere is going to bend the radio waves and speed them up, slow them down, and that's going to also make the source appear like it's not where it is. You know, when you see like a star twinkling in the sky, this is kind of the same thing. It's like a kind of scintillation almost, but it's speeding up, slowing down, bending of the light as it passes through a medium. So we have the troposphere, ionosphere. The other thing then is, we think we know where the telescope position is, right? And so we know, to expect that it reaches A and B at the same time. But what if, our GPS location of the telescope is a little bit wrong? So even if it's like a small, like say a few centimeters off, a few centimeters is very relevant, because the wavelengths that we're looking at in radio are typically, centimeters or smaller or so, or sometimes bigger, but around about the centimeter mark. So it's like a whole wavelength worth of fake delay if your antenna position is off by a centimeter. That's terrible. So that'll tell you that the source is way off from where it actually is. So yeah, there's not only the troposphere to care about, but we also have to know about the antenna position. And then other things that can speed up or slow down our interpretation of the arrival time are things in the hardware of the telescope. So you have, your receiver, and then you have your front end and back end, and there are cables, and cables don't carry the information, at like speed at like infinitely fast. So differences in the hardware of telescope A and B will cause differences in the perceived arrival time. It's not real differences, it's just differences, apparent differences. So we have to actually consider all of these things, right? So you remember before, this term here down on the bottom left, this is the arrival time difference, and it's made up of a contribution of the actual direction on the sky. So if it were at the midway point, that would be 0. If not, it would be something else. And then all of these other things. So BL, this is baseline. This is the antenna position, essentially. Then you have speeding up and slowing down because of the ionosphere, speeding up, slowing down because of the troposphere, instrumentation, so this is the hardware, the structure of the source, and then you have an error term from just every signal has an error term, right? So that's just the thermal error. So all of these are contributing to speeding up or slowing down our signal, such that we can no longer work out what is the direction of the source just based on the arrival times alone. So we have a problem, right? This is something that we have to deal with in interferometry, and this is why we don't have nice things like a nice simple way of getting the coordinates of our sources. So we can measure. So you will have done a lecture on VLBI now. You would have done correlation, I'm guessing, as well. So you'll know that we can very accurately measure the difference in the arrival times of the signals. And if there weren't all of these residuals, then using that arrival time, we could get the direction of the source. So what we have to do, our job in interferometry, is find a way of measuring and subtracting these contributing factors until all we're left over with is the directional term, so like this geometric time delay. So when we measure the time delay, we can work out the direction. So that's kind of our goal. And to do this, we use phase referencing. So phase referencing is kind of like the adaptive optics of radio astronomy in a way. So imagine you have some target that you want to know the coordinates of, and you can measure the time delay, but again, you have all of these residual delay terms that's going to mess up your directional establishment. Unless I put M here because it's maser, because I like masers, but this can be any target that you want. And let's say like nearby there, you have a quasar, so Q. And the quasar has known coordinates from the reference frame. So I mentioned at the start, there's been these radio source reference frames that have been established, and this is kind of one of the reasons why we need those. So let's say you have your quasar and it has known coordinates. Then you can measure the time delay, signal arrival time delay at antenna A and B for the quasar. You know what to expect as a time delay from the location, because you already know the coordinates of the source. So if you subtract the measured time delay and the expected positional time delay, or the time delay you'd get from its position, so this term, that leaves you with all of these here. And so the very kind of basic way of understanding phase referencing is you're gonna measure these residuals, all of them here, and you're gonna assume that the maser has all the same residuals, and so you're gonna measure the residuals for the quasar, use those calibrations to calibrate the maser. Then when you measure the time delay for the maser, you know this, you've subtracted those, and it leaves you just with the directional term, which will tell you the direction of the maser with respect to the direction of the quasar. So it'll give you the position difference between these two. And this will be relative astrometry, so relative to the quasar, but this technique of applying the delay residuals from the calibrator source to the target is called phase referencing. And again, I have to emphasize, phase, delay, is the same. I want you to think of them as the same thing for now. When you start using these techniques and stuff, you'll have to start thinking more in phase. But just for now, I think it's much easier to think in terms of the delay in the arrival time of the signal. So yeah, phase is what we really use as vocabulary for many reasons, which I won't really go into. So yeah, this is the kind of the basic concept of phase referencing. And the practical concept of phase referencing, because you can't look at the quasar and the maser at the same time. So if you're working out these residuals using the quasar and you want to apply them to the maser, you can't measure them for the quasar and apply them to the maser at the same time. So we use this technique called fast switching, and I'm just going to go through this quickly here. So this is the time, the timeline of your observation. And so for some of the time, you look at the quasar, and then you slew the telescope, that's this gray line. You look at the maser for a bit, then you go back to the quasar, and you go back to the maser, and you do this fast switching with the telescopes. So all of the telescopes, so you have like a telescope here and a telescope here, and they both fast switch like that. You can see cool videos of this online if you look it up, or if you go and see a radio telescope that's doing phase referencing, you can recognize that it's doing it because it'll be doing this on like minute time scales. So what the kind of timeline of phase referencing with fast switching looks like is, first all of your telescopes going to look at the quasar, and this has, we already mentioned, it has a known position, so from the signal arrival times we can work out the residuals. So we work out the residuals for this time here. Then we look at the target for a bit, so the maser, and we don't really do any math or anything, we just look at it. Then we go back to the quasar and we repeat the process. So we measure the arrival time difference, we know what the arrival time should be just based on the direction, so we work out the residuals. So we work out the residuals for this time and this time and this time, and everyone knows the weather is changing all the time, right? So the residuals, because they are involving weather stuff, the residuals will be changing over time, especially this term here, the tropospheric delay residual. That's going to be changing pretty quickly, like minute time scales or so. So if you want to, accurately measure how this phase term changes over time, you need to measure it more frequently than it's changing. So when you do that and you measure the residuals at this time and this time and this time and this time and this time, you can then interpolate those solutions or those calibrations to the time where the telescope is on the maser, and then apply those to the maser. And so there's literally, measuring a number for this and subtracting that number from this, essentially. And I want to convince you why it's that easy, okay? So if you take this, the total arrival time difference at A and B for the maser and for the quasar, and all of these residual terms, and subtract everything for the maser from everything for the quasar. So because the signal is coming from different points on the sky, you'll have a time delay from the geometric time delay from the direction, which is the first thing we talked about. Remember, if the source is coming from the midway point, there'll be no delay. If it's offset from the midway point, there'll be some delay. So we're expecting to have some kind of difference in the arrival times just coming from the direction of the sources. And all of the other terms, then we deal with them. So the baseline error from expectation for the maser minus the baseline error expectation from the quasar, the ionosphere delay residual for the maser, ionosphere delay residual for the quasar, and we deal with them like that. So this is where the kind of magic happens, actually. If you think about it, because we're using the same array, so even if we have a positional uncertainty in this telescope and our baseline is not perfectly well known, that uncertainty, so that discrepancy will be the same for the maser and the quasar, because we're using the same array to look at these two different objects. So even if there's a residual, the antenna position residual for the maser and the antenna position for the quasar will be the same. So one thing minus the same thing equals 0. So we can cut that out. Then, because these two objects are pretty close on the sky, so when we're looking at them, we're looking through the same. So if you imagine your telescope B, and there's a very small angular difference between these objects, when you're looking at them, you're essentially looking through the same patch of sky. That wouldn't be true if the maser was over here or something, yeah? So the ionosphere in this direction would be different to the ionosphere over in this direction, probably. But if they're close enough on the sky, then we can assume that or it is the case, that the ionosphere is the same thickness or whatever in the direction of the maser and in the direction of the quasar. So again, the delay contribution, even though we don't know what it is exactly, we haven't worked out a number for it, because it's the same for the maser as it is for the quasar, they cancel each other out. Same with the troposphere. As long as we're looking through roughly the same clouds or perfectly clear sky or whatever, as long as the two objects are pretty near to each other on the sky, so this assumption works out, they'll cancel out. Of course, we're using the same hardware, so it doesn't matter that we don't know what delay is happening in the hardware, because the delay will be the same for the maser and the quasar, because we're using the same hardware. They'll cancel out. And assuming that they are point sources, so this last term comes from the structure of the source. Not really necessary to go much into this as to how the structure of the source changes the delay, but assuming that they're point sources, this is also the same for the maser and the quasar. And as you would have probably seen in a lot of the talks, most VLBI sources that we look at are point sources, because that's kind of all you can really observe with VLBI. You can't see extended emission very easily. So the majority of sources will be point sources, especially in a reference frame source. So they'll cancel out. the thermal error terms won't cancel out, right? Because these are kind of random noise fluctuations in the signal for the maser and random for the quasar. But as long as your maser and your quasar is bright, then the noise becomes kind of irrelevant. So these hopefully are small and you don't have to worry too much about them. So that leaves us only with the directional terms. So if we measure the time delay for the maser, the time delay for the quasar, subtract them from each other, that should give us the positional difference between the maser and the quasar. Or, if you want to think of it in time delays, the equivalent time delay you would get from this geometric difference in source locations, which is then, basic trigonometry, essentially. And this is what we call relative astrometry. So the phase difference gives you the separation between the maser and the quasar. And I mentioned before about this fast switching. So when you switch from, say, let's just jump back to here a second. When you switch from the quasar to the maser and then back to the quasar, that's called one phase referencing cycle. And so these phase referencing cycles must be done faster than these error terms are changing, right? Because if you look at the quasar and you measure your residuals, then you go to look at the maser, but the weather has changed, then these terms no longer are the same, so they don't cancel out anymore. So you need to be repeating this process, this phase referencing, so fast switching and interpolating the solutions. You need to be doing that faster than the weather is changing. And we call it the coherence time, how long the signal stays coherent. So this basically means the fastest changing error term here is typically the troposphere. It depends on which frequency you're working at, but typically the troposphere will be the most quickly changing one. So the higher frequency you go with your observations as well, the more quickly the troposphere changes. So the more quickly you have to do this fast switching between the sources. So just to give a few examples, I think at like C-band, so the frequency of the antenna in Coherence, the coherence time is for C-band in like decent weather is you have a good couple of minutes, like five minutes, maybe even go as far as 10 minutes if you're super lucky. It depends on things like weather or whatever, but we're talking like minutes time scale. If you do 22 gigahertz, so the water masers that I talked about a few days ago, then your coherence time comes down to about a minute, maybe two, if you've got good weather. So you have to switch the antennas more quickly. If you go up to like 100 gigahertz or so, and you're with VLBI, so this is done with, for example, the Korean VLBI network, you have to really either switch crazy fast, like less than a minute, or do some other special techniques beyond phase referencing. So yeah, the coherence time will limit how you do your phase referencing and how easy or hard it is to get your relative astrometry. So with that in mind, this idea of coherence time limiting you can't really have your maser and quasar far away because the telescope takes some time to move from one to the other, right? So that's going to limit how quickly you can move back and forth. So that's one reason why the maser and the quasar need to be close together. The other one is they need to be close together so that these conditions are true. So that the sky conditions, so the ionosphere is similar along this line of sight as it is along this line of sight. If they were really far away, like I said a minute ago, they wouldn't be the same. Like the ionosphere looks differently over here than it does over there. So the quasar and the maser, or the quasar and the target, need to be pretty near to each other. The other requirement that we have for getting the coordinates of our target is that quasar that we're using as a phase reference has to have known coordinates, right? So let's say now you want to look at some maser in the sky because it's cool for some reason, and you want to know its coordinates, you want to do phase referencing and relative astrometry, you better hope that there's a quasar nearby to your target, right? Otherwise, you won't be able to do phase referencing. So what radio astronomers need when they're thinking about astrometry, and this is, it's necessary for astrometry of your source, you need to have a big kind of catalog of quasars, reference sources, that are reference points in your reference frame, so that when you get the relative position of your maser to that quasar, you can then work out the coordinates of your target or your maser based on the offset from that reference point quasar. So we need a large number of, it's written here, we need a large number of quasars with known coordinates to do relative astrometry in interferometry and VLBI. There's a lot of people compiling these catalogs so that we can do this, and it's really thanks to their help that radio astrometry can be done. And just to give you an idea of how these quasars, these reference sources, are typically found, because you can't really just point an interferometer at the sky and hope you see something. It takes a lot of data reduction time, a lot of data in the first place. So you don't want to waste time looking at patches of sky where there's nothing. So the way that these reference source catalogs are compiled is, first you do a survey with like a single dish radio telescope, just to look for, roughly where things are in the sky. Single dish radio telescope doesn't have great positional precision, so you're talking maybe tens of arcsec positional accuracy on the sources that you find. But it's a good start, right? From that good start, then you can use a connected element array like the VLA or ATCA to then get a better holding or a better, more accurate position on the source. So then you can get down to like tens of milliarcseconds or arcsecond, subarcsecond scale, which is much better than tens of arcseconds or minutes or so. And a few examples would be, so you have to do this both in the north and in the southern hemisphere, right? So you need telescopes doing this in the north, telescopes in the south, and then adding them together to get your total map. So in the north you have the survey by the very large array, which is imaged here, and in the south you have the ATCA array, which is doing the equivalent survey for the south. So then you have a catalog of radio reference points, reference quasars, to reasonable accuracy, but it's not good enough. So then you follow those up then with VLBI in the final stage. So this is done in the north primarily with the VLBA, but not just the VLBA. So there's also the EVN, Kava and Vera. Like a lot of the different arrays specifically have time for doing these calibrator searches. And also, in the southern sky, there's only really the LBA. It's the only VLBI in the southern sky, so that's the choice there. And Petrov is Leonid Petrov. He's probably one of the most kind of important people in this work, and he's compiled like huge catalogs of reference sources. So this guy is like super crucial for radio astrometry. You'll definitely reference his papers when you use his reference sources. So yeah, that's how you kind of compile the reference source catalogs, which you then use with your relative astrometry to get the coordinates of your target. And the reason why this is kind of important is because, without doing that, you get an image of your source, because you can self-calibrate on the source, but you won't know where it is on the sky. And let's say you want to know, that you have some radio source, and you want to know, let's say you have some masers, and you want to know where they are in the context of the star-forming region. So if you don't have the coordinates, because you didn't phase reference or do astrometry, you can't tell where is your source in the star-forming region. So it's kind of straightforward, but you see why it's totally necessary. So here's an image from ALMA of a star-forming region called G358. And so your ALMA image that you get at the end has coordinates in right ascension declination. They're cut off here because it wasn't, there was a subfigure in the paper. But yeah, so your image that you get will have coordinates, and so you know where things are in the image. Then these are LBA observations of methanol masers in this region, which were also phase referenced and used relative astrometry to the same quasar actually. So because we're both using the same reference frames, and that means both of our images have coordinates because we did relative astrometry. That means we can know where is this region on there, and it's important because the ALMA image covers a large region at like pretty good resolution, but the VLBI image covers a very small region with very high resolution. So this is the maser emission, and we want to know where it is in here. We know the coordinates, so that means we can overlay basically these two images together. And these methanol masers were in G358 MM1, which is this bright one here. So this is kind of clear, how important knowing the coordinates of your source are. And this is a little bit more challenging in VLBI and interferometry, but if you know your phase referencing, if you know your fast switching techniques and stuff, and if you remember your coherence times, then it shouldn't be a problem, and you can do this kind of work. And the interesting thing then is you can image these things multiple times and use the same coordinate system and phase referencing, and then you can see how these things move in the sky. So you start to see things like expansions or whatever. And I showed an image before or a movie before, right, of these masers doing cool motions and stuff. So those would have been phase referenced so that image is always on the same coordinate system. Okay, so that's all I have for you today. I hope a lot of that was pretty much straightforward, but I think it's pretty important to get the idea of phase referencing. In VLBI radio astronomy, astrometry is one of the things that is super useful. Because of the high angular resolution we have, we're one of the few kinds of astronomy where you can actually see skyplane motions, because these masers are very small. In a couple of months or so they will have moved, and we can see that because we have astrometry and very high angular resolution. So yeah, do astrometry, it's very good. And if you have any questions, please either ask the instructors or maybe put them on the Slack, and I'll get to them. Okay, thank you very much.